So, are we on?
Oh, yeah.
Assume Vj is an MRA of L2 of R with scaling function phi. Okay, I've already written down the definition. I think I'll save chalk. One of the key features was that the VJs were an increasing sequence of subspace, closed linear subspaces of L2 of R, whose intersection was 0, and when you take the union, the closure of that union was all of L2. And so let's draw what that looks like to some extent. And you kind of start at V minus infinity and get a good drawing. So let's begin with V0. Let me draw it this way. And then let me draw V1. And that'll be V1. And V1 contains V0. And then there's something which I'm going to define explicitly and carefully, but which I think most of you already know also, the orthogonal complement of V0 in V1. And let's call that W0. And then let's look at what V2 is. That's V1. Well, V2 contains V1. So I'm going to draw it in this suggestive way. And that's V2. So let's look at the orthogonal complement of V1 in V2. And so that looks like this. That we're going to call W1. And then, of course, we can play this game forever and ever, and that's what one does. So I've got V2, and now I'm going to make V3. Well, this is great design issues here. How you want to do your living room. So there's V3. And we're going to look at the orthogonal complement of V2 in V3. We're going to call that W. And we proceed forever and ever. And one notices something fascinating. It's elementary, but it's fascinating. Namely, we have that V0 contains V minus 1, contains V1, etc. But the W's don't work that way. It looks like we're being symmetric, but we're not. The W's are more or less disjoint. And in a way that we're going to make precise, and this sort of fills up all of L2. And in a way that we're going to make precise, we're going to have that L2 of R is actually going to be like a direct sum of all of the WJs. So that in itself is interesting, and as I mentioned, elementary. Okay, let's quantify some of that stuff now. and the following way. So this is our running assumption. We're assuming the VJ is an MRA. And what we see happening is when we form these W's, this is what they look like. Well, let's, since we want to be careful when we state the theorem and prove that part of the theorem, I'm going to say but I haven't stated any theorem yet, I'm just laying some groundwork. Let Wj, basic assumption it's the VJs are an MRA. Let Wj be the orthogonal complement of Vj in Vj plus 1. By the way, Tom was asking during the break why, when I defined the conjugate mirror filter, I had it equal to 2. Well, that's practically idiosyncratic. I mean, a lot of people do have it equal to 1. But this whole thing with an MRA, basically, Ingrid Doboshif was one of the inventors of the field, has her MRAs numbered oppositely. So basically, and she has reasons for doing that. But most people, although not all of the best people, do it this way nowadays. So there are these little idiosyncrasies that filter in. So what do we mean by orthogonal complement? Well, this means, recall by hypothesis the Vj's are closed subspaces. This means Wj is a closed subspace of Vj plus 1. And Vj plus 1 has the direct sum decomposition. I'm going to write it and explain it. Decomposition Vj plus 1 equals Vj Wj, and that is, it's an orthogonal complement. That is each f in Vj plus 1 has a unique decomposition, has a unique decomposition f equals fv plus fw, where fv belongs to Vj and fw belongs to Wj, and they're orthogonal. And I wrote the plus there. And f v perps f w. So that's the type of thing we do. Now, fact, f t, even though it's not correct to use this way, but since I'm going to use f of 2t, or be consistent, f of t belongs to wj if and only if f of 2t belongs to wj plus 1. Now remember, this was a property that was part of the definition of the multi-resolution analysis with the VJs. But we saw that the VJs are fundamentally geometrically different than the WJs, so there's something to prove here. And proof. Well, let f be in Wm, say. Well, what does that mean? Then f belongs to Vm plus 1. Since Vm plus 1 is equal to Vm, and I mean here the orthogonal exponent, Wm. So therefore, since f is in Vm plus 1, I use the fact I'm dealing with a multi-resolution analysis. So therefore, f of t over 2 belongs to Vm. And Vm, of course, is equal to Vm minus 1, orthogonal direct sum of Wm minus 1. On the other hand, and I'm going to go to my left. F of t over 2 perps Vm minus 1. Okay? So f of t over 2 is in Vm minus 1 because f is in Vm plus 1. And now I want to show that f of t over 2 perps Vm minus 1. Since, why? Well, since if I just look at what it is, I've got 2, I'm in the m minus 1 range, so m minus 1 over 2, the integral phi of 2 to the m minus 1 t minus n, and then 1 over the square root of 2 f of t over 2 dt. Well, that's equal to, if I do the change of variables, if I let u be equal to t over 2, then when I get that this is equal to 2 to the m, and I might be off by something or other here. I'll check it after I'm done. The integral phi of 2 to the m u minus n f of u du. Because if this is u, so u is equal to t over 2. So t is equal to 2u. So I get a 2 to the mu minus n. And then I have a dt is equal to 2 du. So I've got a 2 out here, and that come on right? 2 to the m over 2, 2 to the, oops, minus 1 half, and then times 2 to the minus 1 half, and then times 2, so it's minus 1 times that, so I have 2 to the m over 2. Well, what do we know about this? Well, F is in WM. And this guy here is in VM. So this is equal to 0. And so what we do have is we've got that F of T over 2 does perp the M minus 1. So therefore, F of T over 2 perps that guy there, so that's in W M minus 1. And this is a little sick, of course, because I'm not the first time in my life I've gone backwards, but I was out to prove that if F is in here, that F of 2 of it is in there. But that's the same as proving that if F is in there, that F of T over 2 is in J minus 1. So easy, but there are things to be proved. Okay. Now, I mean, that picture I have here is very telling because we really use that. And so I'm going to leave that up there, and let's start another calculation here. So this is one calculation. So another calculation fact. First of all, phi minus 1, 0. If I just write that out, what is that? Well, phi minus 1 of 0 of t is equal to 1 over the square root of 2 phi of t over 2, right? Because the n is 0, and we're getting minus 1 there, so that's 2 to the minus 1, and this is 2 to the minus 1, 1 half. And so therefore, this implies that phi minus 1, 0 belongs to v minus 1, which is contained in v0. Through all of this, I'm assuming I'm dealing with an NI array. So since it's in v0, I can write down an orthonormal expansion. This implies that 1 over the square root of 2 phi of t over 2 is actually equal to the sum h0 of n. It's got Fourier, it's got orthonormal basis coefficients, phi of t minus n in L2 of r. So I'm using the definition of the multi-resolution analysis all the time here. This is the part that says that the translates of the phi are an orthonormal basis for v0. Where, what is h? Where these guys here, h0 of n, and this is by basically Hilbert space theory, we know that these are in L2 of z, and they're equal to h0 of n is equal to the integral phi minus 1, 0 t phi of t minus n conjugate dt. And well, I'll just, so that's all true. Now, once we have that, that's, if I take the Fourier transform of this, so take the Fourier transform of that, and what do we get? We get to obtain obtain that, well, you remember from the first day of class, here we're dilating we're spreading it out. When you take the Fourier transform, you're squeezing it in. And so we get then square root of 2 phi hat of gamma is equal to h0 of gamma phi hat of gamma, where h0 of gamma is this guy here, h0, and e to the minus 2 pi I n gamma. And this is in the convergence of L2 of so this is in the convergence of L2 of I hat. Wow. Look at what we proved over here. We proved that in this situation, where you have that formula, then the H0 is a CMF. So, well, I got the one, I should have left it over here.
Inside.
Oh, but then I did that wrong. I do have the 1/2. When you do, I forgot the 2 here. Sorry. Thank you for bringing that up. Yeah, that was the whole point of being with the t over 2 here, it goes into 2t. So I get exactly 1. This is 1, and therefore H0 is in L infinity of the torus, and H0 is a conjugate variable. Okay. So now let me state the basic MRA here. Theorem. I'm just going to call it the MRA theorem. I've already talked about the history of it, so I will not tell you about that right now. So let VJ be a multi-resolution analysis of L2 of R with scaling function phi. And in L2 of R. There is a constructible function psi. You can take it in W0, but you don't have to say it that way. But anyway, you know, 2 of R such that psi depends on phi and the multi-resolution analysis. Psi Mn is an orthonormal basis for L2 of R, and And this is the wavelet orthonormal basis for an MRA. Well, let me just put an and here on the end. Then we write, in fact, we can actually write down a formula for psi. In fact, set psi of t equal the square root of 2 times the sum h1 of n phi of 2t minus n in L2. We have a nice high chalk here until now. So L2 of R. Now notice phi of 2t minus n is in V1, 2 to the 1. And so this guy here turns out not to be in V0, turns out to be in W0. So in fact, set psi equal to that, where for all n, h1 of n is equal to minus 1 to the n plus 1, h0 minus n minus 1 conjugate, where and where. Now, by the way, one sees a formula like this, and sometimes, depending on how you do your calculation, they're all correct, or can all be correct. You might have a minus n plus 1. It depends on various things. So where for all n, h1 of n is equal to that, and where h0 of n is the sequence of Fourier coefficients of the CMF H0 which in turn is a solution of the frequency scaling equation that we just wrote down in the square root of 2 phi hat of 2 gamma is equal to h0 of gamma phi hat of gamma in L2 of R. Okay, so that's a mouthful, but you can see that it gives a tremendous number of orthonormal bases. I mean, prior to wavelet theory, you talked about the Hermite functions to give orthonormal bases for L2 of R, and I suppose someone, if they were given the hash system on T, thought about doing it, could have written out the hash system as we did last time for L2 of R. But this is a systematic way of making orthonormal bases for L2 of R, given MRAs. And it turns out there are tons and tons of MRAs. One of the interesting things is But you can also make zillions of orthonormal bases once people start thinking about it with non-MRAs. And so once you go to higher dimensions, there's a huge MRA theory, which is a very natural extension of this, but then a very interesting, which I've talked about before, geometrical theory of providing lots of different wavelet orthonormal bases that don't come from MRAs. Okay, so we're going to prove this. We will not finish the proof tonight. What's that? Well, I could, if I could finish it tonight. We will not finish it by the time I'm going home. Well, I'm not. Basically, what I want to do is, I mean, I think you've noticed, I could finish it in 10 minutes, but I do want to provide the details. I know that might be remarkably, stultifyingly, remarkably is not the right word, stultifyingly boring, but I wanted to show that there's a lot of interesting structure involved, and sometimes when you read a book, especially by a smart person, unless you sit down with epoxy on a chair and go through the details, you don't realize all the details. There are a couple of sort of philosophical points, and I'm not going to BS, but basically one notices even here this interplay between Fourier series and Fourier transforms. I mean, we're just in the statement of it, we're talking about Fourier coefficients and Fourier transforms, and that essentially goes to the heart of sampling theory. And sampling theory, in some sense, regular sampling theory, is a special case of all of this without the scaling. Once you go to the scaling, then it allows you to get orthonormal bases for all of those who are. Okay, so proof. So part A. Yes. Let F be in V1. By the way, there are some points I'm not going to prove all the details for, and there's an interplay here for having a general fee, or one that has certain restrictions on it. One usually sees the restrictions in, for example, in the last paper in the transactions. And, you have certain growth conditions, and they arise very, very naturally. And I'll point out where they do arise. And that's actually a place where there's a lot of flexibility of where you want to have the decay conditions arise. Now, I shall point that out. In fact, one's going to happen very soon. So let F be in V1, and then F, oh boy, if and only if, that's all I can get rid of. If and only if F is equal to the sum over N of F 2 and 1/2 phi of 2t minus n, and then 2 and 1/2 phi 2t minus n. And so that holds if and only if, taking the Fourier transform, f hat is equal to sum over n, f 2 and 1/2 phi of 2t minus n. And then taking the Fourier transform, I get 1 over the square root of 2 phi hat of gamma over 2, the two t's go this way, And then I pick up an e to the minus 2 I n over 2 gamma. In fact, over here, in this calculation from the previous part, the reason I was able to extricate the H0 when I took the Fourier transform was I had the phi of 2t minus n, and so when I take the Fourier transform of that, I'm going to pick up an exponential. And so that's what's going on here just as well. Now this is equal to 1 over the square root of 2, doesn't depend on that, phi hat of gamma over 2, and then f, which depends on little f, of gamma over 2. So that's the rest of it. Okay, so that's all of this and this. Where we want conditions on phi to ensure F is in a good space. Now here I'm showing tremendous hypocrisy because I just self-righteously said we're going to show all the details. 30 seconds later, the cock crowed. It reminds me when I was a graduate student, I was fortunate enough to have some great lecturers, but one of whom was Andrew Gleason, who I think I mentioned solved the Japanese code in World War II, told me by Captain Dyer, who headed the team in Hawaii. But Gleason was a spectacular lecturer and taught analysis at Harvard, and I had already taken several topology courses there, and it was always ended up with, you do this, you do this, you do this. So I thought I'm finally going to take this advanced topology course with Gleason, and I'm actually going to see proofs. And sure enough, for the first month and a half, Gleason was proving everything. It was spectacular. And then, it was a fall semester. By mid-October, Gleason saying, then you do this, you pull this, you do this. But basically, there's the interplay on the function you take phi in your MRA, and the type of decay it has, in order to say something about where this space is. And let me do, I did one or two little calculations out, but basically, if you look at this function here, so this is an aside to the proof, it's not part of the proof, but this is just an aside to see what you have to do. We want to look at these coefficients and see if we have any control of them. Okay? So, just the calculation, we have that f 2 to the 1/2 phi of 2t minus n. That's equal to, by Clauserel, f hat, and then 1 over the square root of 2 e to the minus 2 I n over 2 gamma, phi hat of gamma over 2. And so writing that out, that's equal to 1 over the square root of 2, the integral f hat of gamma, phi hat of gamma over 2, e to the minus 2 I n over 2 gamma to gamma. Now, what we'd like is, I mean, in the best of all worlds, what we'd like is the absolute value of this to be, this is a wish, would be less than or equal to Rn, where we have control over the Rn. Something like the sum Rn finite. That would be spectacular, or even this. Because we'd be able to do something with that. But what can we say just about this guy by itself? Well, just that guy by itself, f hat in L2, because that's where f is, and phi hat in L2, because that's where phi is, that implies that f hat of gamma, phi hat of gamma over 2 is in L1 of our hat. Well, that's pretty good, because what that says is, that says that therefore, the integral f hat of gamma, phi hat of gamma over 2, e to the minus 2 I t gamma to gamma is in A of R. Remember, A of R is contained in, these are the absolute convergent Fourier transforms. So that's contained in C sub 0 of R. So they have decay. So there's a chance. But what you need now is, and this shows one of the things you need, what you need now is, if I was just dealing with one f, then I could choose my phi in such a way to get spectacular decay. But what I really need is I have to have something true for all f's in this class V1. But that's rather arbitrary, except for the fact that V1 is really defined in terms of phi. So you see there's a really nice analysis problem here. Since the V1s, the union of all the Vj's is dense in L2, but each one of those Vj's could be awfully skimpy. And so that's why I'm not going to be compulsive here. But there are very nice problems to do here, which you don't really see done in too many texts. But the people who initiated the theory certainly understood this, which is why they say, well, you need some sort of condition on the phi. Okay, so, but even this, so this is without working at all, we get it in A. And those are going to 0. But we really would like to have more control than that, because A isn't even in L2 necessarily. I mean, it's not in L2. And if you just had to do it for one function f, then you could. It's easy to get really fast decay. But if you wanted to get it for all f's in V1, that's almost like getting it for all f's in L2. Well, not exactly. Because the V1s, the union of them is dense, so if you come back and use the fact that the V1 is really defined in terms of the phi, then you can do some estimates here, see what you can do. Yeah, basically they use various conditions, but I would like to, I've never done it myself, but what I just said, I think is a way to really, a way to really nail it. To use, you start off with a multi-resolution analysis fee to see what V1 is really made of in terms of those fees, and then go into the analysis with that really coming from a fee, you see, when you expand it, with that fee there, and then maybe then, I mean, it's awfully hard to, see, that's the reason I did Plancherel here, so that I could get this in L1 to be able to get some sort of smoothness in decay. But using the fact that F comes from fee, then I have a chance of doing better, or I can take a fee that has a certain property and sort of optimize the decay. That's the idea. I mean that, I think that's worthwhile doing, but I'm too old to do it. So that's the aside. Okay, so we have that F in V1, if and only if this holds, and I'm going to assume that this one periodic function, capital F of F, is relatively nice to proceed with my calculations. And you can assume phi satisfies certain conditions so that it is as nice as we need it to be. Okay. Now, let's see. I'll erase this. So, B. Question? So, recall F is in W0, if and only if F perps V0, and we'll show that F is in W0 if and only if the sum of F hat of gamma plus K phi hat of gamma plus K conjugate is equal to 0 almost everywhere. So let's do that. So there's a little bit of work here. So note that F per V0, if and only if the integral F of t, phi of t minus n, conjugate, et, equals 0 for all n. If and only if the integral F hat of gamma, phi hat of gamma conjugate, e to the 2 pi I n gamma d gamma equals 0 for all n. If and only if, can you get it over here, Brent?
Yeah.
If and only, write one more line here. If and only if, now I want to spread this down, I'm going to sum over k's. Of the integral from 0 to 1 of, I make the change of variables, F hat of gamma plus K. Need another piece of chalk. F hat of gamma plus K, phi hat of gamma plus K, E, e to the 2 pi I n k, n gamma, d gamma, is equal 0. Okay? And all I've done is, well, you can see what I've done. I've just made the change of variable here. So I'm just summing over all the guys going from, all the k's going from 0 to 1. But the reason I don't have to worry about gamma plus k in here is that because either the 2 pi I n k is equal to 1. The box.
So that means they conjugate of phi hat.
Oh, yeah. And that holds if and only if the integral from 0 to 1 of this sum inside of k f hat of gamma plus k phi hat of gamma plus k conjugate e to the 2 pi I n gamma p gamma is equal to 0 for all n. Now, this function here, g is one periodic. And let's look at its L1 norm. And its L1 norm as a one periodic function is less than or equal to the integral from 0 to 1, and I can take the sum, I'll go all the way inside, k f hat of gamma plus k phi hat of gamma plus k, don't need the conjugate now. That's less or equal to that. But this, by making the change of variables, this is now less than or equal to the integral over all of r hat of f hat of gamma phi hat of gamma phi gamma. Well, f hat and g and phi, right, because I've made the change of variables, and now I'm summing, I get it over, so bring this on the outside, switch summation and integration, and then I then have the sum over k's going from k to k plus 1, et cetera, et cetera. But this is an L1. You get two L2 functions multiplying times each other. This is less than or equal to f hat in L2 of r hat and phi hat of L2 of r, which is finite. And so G is an L1. So since G is an L1, and we have this is equal to 0 for all n, we can therefore say, let me keep that, so, where were we here? We have that f perps it if and only if this holds for all n. Well, G is an L1 of the torus. These are its Fourier coefficients, and all of them are 0. So, since G is in L1 of the torus, then asterisk over here, then asterisk implies G is equal to 0 almost everywhere by the uniqueness theorem. Or Fourier series. we wanted to prove. So we did it. So therefore, star holds. Therefore, star holds. So every little step we have to work for. I mean, there's something involved there. But on the other hand, we have it. Now, so we've proven now that F is in W0 if and only if this holds. Now let's go one step further and show that, what am I up to? That pad B, pad C, pad C. We now show that F is in W0 if and only if. See, W0 plays a big role for us because that's where we're going to pluck the psi from. If and only if F sub F H0 conjugate plus translate by minus a half of F sub F times the translate by minus a half of H0 conjugate is equal to 0, where F sub F is the Fourier series associated with F as defined in part A. Okay? So we want to show that. So what we're going to do is, to do this, hold on a second. Okay, so we've gotten that we have star over there, and now to this end, substitute phi hat, which we already know is equal to 1 over the square root of 2 phi hat of gamma over 2 times H0 of gamma over 2 into star. Okay, so we already know this is true. We proved that because we started off with a multi-resolution analysis. And we already know that F is in W0 if and only if star holds. So since we're going to substitute that condition, which holds all the time, into this criterion here. And we have that therefore 0 is equal to the sum over k, f hat of gamma plus k, phi hat of gamma plus k, okay, that's just star, And now I'm going to plug this into there. So that's equal to, oops. Hold on, don't leave. Oh, because of the way we did the f hat and the Fourier series associated with it, this is equal to 1/2 the sum over k of f sub f of gamma over 2 plus k over 2 h0, I'm up here now, h0 of gamma over 2 plus k over 2. And then I have, I've got this one times this one, but I've already, I've translated it. So I have phi hat of gamma over 2 plus k over 2 quantity squared. Okay. Now, so that's just what we've done so far. And now this is equal to, let's just let the gamma over 2's be lambda. And now I'm going to write this as a sum, and since it's equal to 0, I can get rid of that. And so now this is equal to, I'm going to run this over even and odd again. It's equal to sum k even plus the sum k odd. And we're just about done. So I can pull, with k is even, since it's a one periodic function, this is equal to f, a lovely little bug here in the rack enjoying the chocolates, f sub f of lambda, and then again, h sub 0 of lambda. And then the sum of all these guys, phi hat of lambda plus k. So that's for the even case. And then for the odd case, it's the same sort of thing. I pull out plus f sub f of lambda plus a half. So I've got k equals, k is odd, so it's 2m plus 1. So I pick up that half there, because I get an m plus a half. So f sub f of lambda plus a half, h0 of lambda plus a half, then the sum of phi hat of lambda plus a half plus m squared. And now these are both equal to 1, and so I get exactly this guy here, double stuff. By orthonormality, we have okay, so this was cruel and unusual punishment tonight, sorry. I think I am going to stop here now. But what we've done is we've kicked the living daylights of what it means for F to belong in W0. And that's a big forward step. In the interest of reducing animosity from that direction to this direction, I think next time I will perhaps be a little more conceptual. Because we've shown that there's this relationship between Fourier series and Fourier transforms relevant. It permeates the whole proof, by the way. But maybe next time I'll just give you the ideas on how to finish it off. Okay? Have a good rest of the week.